Hello again. Let's talk about crossed aldol reactions. Alright, so the moment you have this word introduced into the title, crossed aldol, what that means is that you're going to be reacting different types of carbonyl compounds with each other. So for instance, here we have the enolate version of 2-butanone, but we might want to react this with, let's say, an aldehyde, so different molecule altogether, in order to form the corresponding beta hydroxy carbonyl compound. Now, in order for this to work out, you will first need to make the enolate, and since you're starting with a ketone in this case, you could reduce the temperature to -78 degrees Celsius, use a bulky base to carry out the reaction, and then you introduce your aldehyde to carry the process. And this will be actually a very efficient reaction, because the aldehyde, this particular aldehyde, benzaldehyde, doesn't have any alpha hydrogens. So this reaction will be one of the more smooth and well-behaved reactions out there. And just like benzaldehyde, using ketones that don't have alpha hydrogens will make this reaction be as efficient as possible. You will not run the problem of having an equilibration where the enolate that you prepare starts removing protons from the more substituted side of the incoming ketone or even aldehyde that you may be using. So that has that benefit, right? You don't have to worry about that, and the reaction is pretty smooth and pretty robust. But there will be situations where you might want to use uh, compounds that do have different types of alpha hydrogens, and maybe even the one that you're about to introduce for the second portion of the reaction may have its own alpha hydrogens. So in those situations, my recommendation is that you instead first prepare the enol ether version of the nucleophile by using trimethylsilyl chloride. And so if you want the less substituted enolate, then you use the bulky base at low temperature, and you follow that up by introducing trimethylsilyl chloride. That will trap the less substituted enolate. Alternatively, you can react your ketone with trimethylsilyl chloride from the get-go, as well as triethylamine, and this will give you the more substituted enolate also from the get-go. So once you get to those two products, then you can introduce an aldehyde, a ketone, anything you want. And then notice that this aldehyde does happen to have alpha hydrogens, but the fact that I've turned this from a lithium enolate into just an enol ether makes this molecule less reactive, a lot less basic for sure. So the problem of having deprotonations and forming other types of products is completely nullified. So here instead, the introduction of titanium 4 chloride with your aldehyde will activate the carbonyl carbon of the aldehyde, and it will allow for the condensation reactions to happen, right? So here in this case, the top portion of the molecule is the enolate, or used to be the enolate. The bottom portion of the molecule is what used to be the aldehyde, and needless to say, the aldehyde that got attacked is turning into an alkoxy group. Same thing can be said over here for your more substituted enolate. Introduce titanium 4 chloride with your aldehyde of choice, and you will undergo the condensation reaction. And by the same logic, up here you have what used to be the enolate, now it's a carbonyl compound, and down here you have what used to be the aldehyde, which now it's an alcohol portion, technically speaking, right? But that's how you get these products. And I would recommend, as you're still getting used to this thing, to probably label numerically your carbon, so you kind of see where things go. But as you get more comfortable with that, you might be able to get to it the way I kind of show right here, right? You're kind of like putting them top and bottom, and connecting the carbonyl carbon of the aldehyde electrophile with the alpha carbon of the enolate. So yeah, that's pretty much it for the cross aldol condensations. I just want you to make them as efficient as possible. The reality is that yes, if you have different kinds of protons and you add hydroxide to this, you're expected to get at least 4 different products, and your yields are going to be pretty crap if you do that. Whereas this route of attack is a lot more efficient, and you should be expecting good yields out of these reactions. All right, so this is a short video. I know the last one was a little bit longer. This was a little bit shorter, which is kind of nice. But in the next video, we're going to talk about related reaction. It's technically an aldol reaction, but it's an aldol reaction with esters. So I'll catch you up on that video. Bye-bye.